All right, hello everyone, and welcome to AP Review number 4. Today we're going to be talking about applications of derivatives as that relates to dealing with just kind of functions out of context, f prime, f double prime. Going to go through a little bit of review, show some just examples of applying this knowledge. Remember, this is not necessarily like a full reteach, but a review of certain topics. If there are more things that you need, please email, reach out, let me know what you need. We can spend some one-on-one time. Just be sure you let me know what you need, okay? So let's go ahead and get started with a few review topics, okay? First, we need to remember what it means for function to be increasing or decreasing, all right? Well, function, in this case, let's just refer to f, but whenever we're talking about a function, it could be any name, right? We could say f is increasing. F is increasing when f prime of x is positive. All right. We also know that f is decreasing when f prime of x is negative. Because remember, f prime, that prime is referring to the slope. So we're saying f is increasing when the slope is positive, and f is decreasing when the slope is negative. All right. So for example, if we're looking at a derivative graph, all right, we're looking at the graph of f prime of x. F, the original graph, would be increasing. Let's call this point A. Let's call this value B. And let's call this value C. We could say that that f is increasing. F is increasing on the interval A to B, because that's where a derivative graph is positive above the x-axis, and then from C to infinity. And our original function f would be decreasing from negative infinity until a, because in that section f prime is below the x-axis, and from b to c, because that's where f prime values, the y values for our f prime graph, that means f prime is negative. That means our original function is decreasing. All right. We can also use this to determine where there are local or relative extrema of a function. We could say that f has a, I'm going to just abbreviate here, relative maximum when, now if we just think about what happens on a function when we have a maximum, a function has a maximum, I'll just draw this on the side, a function, like an f graph, has a maximum when the slope or the derivative changes from positive to negative. That means f is changing from increasing to decreasing, right? So we could say when f has a relative maximum when f prime, the slope, changes from positive to negative. And the vice versa happens for a relative minimum. F has a relative minimum when f prime changes from negative to positive. Right. If we use the same example up here, then, if we use the same example up here, f has a relative maximum up here when the derivative changes from positive to negative. We're looking at the derivative graph, so the derivative is measured by the y values here. The y values are telling me the slope of the original curve. So where does my f prime graph change from positive to negative? That happens at b. So in that above graph, I can say at x equals b. F has a relative minimum where this derivative graph changes from negative, being below the x-axis, to above the x-axis. So that would be at a and c, at x equals a and c. All right. Now, this is what's called the first derivative test. You don't necessarily need to know that by name, but this is referred to as the first derivative test because it allows us to use the first derivative to determine where there's local extrema. We also have what's called the second derivative test. The second derivative test will also do this for us. What the second derivative test says is if f prime of x, so the derivative is 0, which means we have a leveling off point on the graph, either up there or down there, we can actually use the second derivative to tell us what's going on. So if f prime of x equals 0 and f double prime, the second derivative of x, is greater than 0, in our minds we think that means that f is concave up. We're in this situation over here. So I should say if f prime of, let's make this more specific, if f prime of a equals 0, and f double prime of a, f double prime of a at that spot, if the second derivative at that spot is positive, that means our curve is concave up, which means we have a critical point, and our graph is concave up. That means f of a is a relative minimum. If f prime of a, so we know that there is a horizontal tangent line at a, and f double prime of a, the second derivative, it turns out, is actually less than 0, then f of a is a relative maximum. We can visualize that over here. We have a horizontal tangent, f, if this is x equals a right here, f prime of a is 0, and the second derivative is less than 0, which means that our curve is concave down. So we have to have a relative maximum. That's called the second derivative test. Okay. Now that leads us into talking about concavity, since I already brought it up, right? Concavity of a function we determine from the second derivative. So I could say f is concave up when f double prime of x is positive. But another way to think about this, the second derivative is positive. This has another meaning. We could say this is when f prime of x is increasing. Because if f prime of x is increasing, its slope is positive, which means its derivative is positive. That's the second derivative. All right. We could also say f is concave down when f double prime of x is negative. In other words, when f prime, the derivative, is decreasing. Now, if these kind of relationships are something that's difficult for you, let me know. I have plenty of stuff we can just work one-on-one with to practice this, okay? So if we're looking at, for example, our first derivative graph, let's say we have a situation like this. Our first derivative graph increases up to a point, decreases down to there. This is our first derivative graph, sorry. We could say here then, f prime is increasing on this interval. So in this specific problem, we would say that the original graph, is concave up from negative infinity until 0. And I'll write that down. So in this specific problem, negative infinity until 0 would be, why did I do a bracket there? I don't know. That would be how we would word that. And then from 0 to infinity, since f prime is decreasing, our original graph is concave down. If we were looking at the second derivative graph, this would be a little easier because we could just, if this was the second derivative graph, we could just look where the graph would be below and then above. The above and below the x-axis would tell us whether or not f prime is positive, being up here, or negative, being down here. All right. I'll get rid of that so that's not overly confusing to what I wrote above. All right. Finally, talking about maximums and minimums of a function. I put absolute in brackets because you won't always in a problem be told absolute maximum or minimum. If it just says, hey, what is the maximum or minimum, we assume that means the actual absolute maximum or minimum. So you might not see absolute. If you just say, what is the maximum, we literally mean the absolute maximum, the maximum. Okay? And a couple reminders how to do that. We need a couple things. We need critical points. So I guess I should put here, we need to check critical points. The critical points, as a reminder, are where f prime of x, the derivative, equals 0 or does not exist. We check critical points and our endpoints. Okay, so this basically leads to a two-step process. We find the critical points, we find the endpoints. Those gives us that gives us the candidates, and then we take the candidates. You'll get a bunch of x values from your critical points and your endpoints. Take the candidates and plug into f. We always plug them back into the function we want to maximize or minimize. Plug into f to find max min. Now, as a reminder, when we're talking about the max min, that refers to the output values, the y values. If I say, what is the absolute maximum? You give me the y value. If I say, at what x value does the maximum occur? Then you give me the x value. But if we're actually talking about the maximum minimum, we're talking about the output values, okay? One note on accumulation functions, just as it relates to the AP exam. One thing that they do really like to do is to take like derivative graphs or derivative things and ask you about the absolute maximum and minimums of those things. Well, if you're just given a derivative, you need to be able to write a function then to give you the kind of f function, right? This is where, in those situations where if we're given a derivative, and we're given an initial value, which is often the case in these problems, we'll see later on, then we need to end up writing something that looks like this, that f of x is going to be equal to f of a, the initial value they give you, wherever that is, plus the integral from a until x of f prime of t dt. So you'll take the integral of the derivative that they give you plus the known initial value, okay? This is just a note. Keep this in mind. This is a big thing we'll see. If we're given an initial value and we're given something about a derivative and asked to find a value, we need to set up our function like this, okay? Let's take a look at some examples. All right. Walk through some examples here. The polynomial function f has selected values of its second derivative f double prime, so it's a second derivative. Given in the table above, which of the following statements must be true? We always want to be able to look at when we see something that's like must be true. So let's see. Second derivative. I'm just going to write myself a note. Second derivative tells me about concavity, right? Second derivative tells me about concavity. I only have specific points. I don't know what goes on. I don't know what goes on between these x values, but I do know these specific points. So let's see. F is increasing on the interval. I can't tell that from the second derivative. That'd be a first derivative question. If I want to know if f is increasing, I don't know that. F is decreasing. That's also an f prime question. I don't have information to talk about whether or not f is increasing or decreasing. I would need to look at f prime for those kinds of things. F has a local maximum at x equals 1. Local maximum at x equals 1. I know that the second derivative is 0. That doesn't tell me really anything about having a maximum or minimum. Remember, for maximum or minimum, I need to know whether or not the first derivative changes sign. I need to know if the first derivative is 0, if I have a horizontal tangent there, those kinds of things. Essentially, this is also a first derivative question. If you want to, it's fun to go back and create what would need to be true to make these things happen. All right. The graph of f has a point of inflection at x equals 1. Now, point of inflection, that's not something we just talked about in the table above. So let's write down a reminder. You can add it to the table above. A point of inflection is when f double prime of x changes sign. And that's important. It's not when it's 0. It's when it actually changes sign. So D says the graph of f has a point of inflection at 1. E says the graph of f changes concavity. See, if f prime changes sign, that means concavity changes. That's the definition of a point of inflection. The graph of f changes concavity on the interval 0 to 2. So basically, does the graph change concavity here, or does the point of inflection happen right there? Now here's what's tempting. We don't know what must be true. We know that the second derivative is 0 here, but that doesn't actually mean that the concavity change or the second derivative changes sign there. Maybe it hits 0, goes maybe it's positive, hits 0, goes positive again, and then crosses negative. I don't know. That just tells me that I have a second derivative of 0 there. That doesn't mean there is a point of inflection there. I can't actually tell that for sure. But somewhere between 0 and 2, does the concavity change? Yes, because my second derivative changes from positive to negative. It's kind of like an IVT question. So there we go. This is the only one that must be true. D could be true, but it doesn't have to be. All right. Number 20, let f be a function with a second derivative given by this thing. What are the x-coordinates of the points of inflection? Hey, look, another points of inflection question. Points of inflection are where the second derivative changes sign. Oh no, what are the x-coordinates of the point of inflection of the graph of f? Well, I'm already given the second derivative, so let me just go ahead and do a sign chart then for my second derivative. All right, what are my zeros for my second derivative? Because a sign chart will tell me where that second derivative changes sign, if I can do this right. So my zeros are at 0, 3, and 6. I'm going to put 0, 3, 6. I'm going to write down my factors, including any power. So x squared, that's funky, but that's x minus 3, and then x minus 6. Sorry, my first x got really crazy. All right, couldn't decide if I was going to do a parentheses or an x, and failed at both. Oh man, that got even worse. Okay, so we set up our sign chart. Now we go through and let's figure out what's going to go on in each of the columns when x is less than 0. Say negative 1 squared, that's going to be positive. In fact, squared is going to be positive all the way across, and that's going to be important for us. When x is less than 0, say negative 1. Negative 1 minus 3 is negative. Negative 1 minus 6 is negative. And then we pick a number between 0 and 3, say positive 1. Positive 1 minus 3 is negative. Positive 1 minus 6 is negative. A number between 3 and 6, say 4. 4 minus 3 is positive. 4 minus 6 is negative. Bigger than 6, say 7, is going to give us everything positive. Now multiply these things together. Since they're factors, that'll give us a positive second derivative, a positive second derivative. So this tells us that my graph is concave up. My graph is concave up. A negative second derivative, negative times positive gives me negative. That means my graph is concave down. And then positive times positive gives me another concave up section. So what goes on? Where are there points of inflection? Points of inflection where the concavity changes, so the second derivative changes sign. That's going to happen here at 3 and 6. Okay, 3 and 6. We actually could have seen that quickly from the second derivative here. Squares are not going to change sign, but at 3 and 6, because each of these terms is only an odd power, these two terms will change sign at 3 and 6. There we go. All right, and as a last example here, particle moves in a straight line. The graph of the particle's position, x of t, so that's kind of like our initial function, right? X of t is position. Position is given up here. The graph has horizontal tangents at t equals 1. Just going to kind of draw that in. And t equals 5. Just kind of draw that in. So what does that mean? Horizontal tangents. That means x prime of t equals 0 there. Okay. And a point of inflection at t equals 2. So what does that mean? At t equals 2, that means x double prime of t changes sign. And I want to know for what values of t is the velocity of the particle increasing. Okay. Now, this is a position graph. Position's our original function. X prime of t equals 0. That's the same thing as saying v of t, then the velocity equals 0. And x double prime of t, that's the same thing as saying v prime of t, or a of t, right? I don't know when is the velocity of the particle increasing. Well, velocity is increasing. How do I know when a function's increasing? I know a velocity is increasing when v prime of t is positive, right? Velocity is increasing when v prime of t is positive. Or what's v prime of t? V prime of t, that's a of t, when a of t is positive. Well, how do I know a of t from this graph? A of t, right, is the second derivative of this graph. So I'm going to be looking for where a of t is positive. In other words, where the second derivative of this graph is positive. Again, I'm looking for where velocity is increasing. Velocity is increasing when its derivative is positive. The derivative of velocity is acceleration. And I know acceleration is the second derivative of this graph, this particle thing I'm given, this particle position that I'm given, right? So in other words, I need to look for the second derivative is positive. What does that mean? I need to look for where x of t is concave up. Where is x of t concave up? We know there's a point of inflection right there. So from 0 to 2, x of t is concave up from 0 to 2. All right. Try some challenging ones to sort of get your mind rolling around these things, okay? Let's go ahead and move to next page. I want you to pause the video, take some time to practice these problems here, please. There's 1, 2, 3, 4, 5 practice problems to do, all non-calculator. Pause the video, and then come back and check your work. All right, let's go ahead and begin. Let's start with this one up here, upper right. If g is the function there, on which of the following intervals is g decreasing? So I write myself a note. Always good to annotate. G decreases when g prime is negative. So I find g prime. What is g prime? G prime of x is, I need the derivative of this, will give us x squared plus 3x minus 70. Right? All right. So I need the factors of that. G prime then, is because I want to do a sign chart, because I want to figure out when G prime is negative. So I got to get my sign chart. Let's do x plus 10, x minus 7. All right. That'll do it, right? So I do my sign chart for G prime, x plus 10, x minus 7. Always make sure you put your zeros in order. My first zero is negative 10, and then positive 7. All right, so I choose number less than negative 10. It's going to be negative, negative. In between these two, I'm going to have positive, negative. And then after 7, I'm going to have positive and positive. Again, this is the first derivative, g prime. So this tells me my graph is increasing and then decreasing because the derivative is negative, and then increasing because my derivative is positive. So where is g decreasing? From negative 10 to 7. Here's the graph of the derivative of f. The graph has horizontal tangents. So it's the derivative of, the graph of the derivative of f. This is the derivative. Always make a note of what we're looking at. This is the derivative. The graph has horizontal tangents at, negative 1. So this graph has horizontal tangents at negative 1, 1, and 3. But this is the derivative. Which of the following values of x does f have a relative maximum? I know f has a relative maximum when f prime changes from positive to negative. I'm looking at the f prime graph. So where does f prime change from positive to negative? Right here. Right there. That's where f prime changes from positive to negative. I'm looking for f, the original graph, has a maximum. So I look at where its derivative changes from positive to negative. Right there. These horizontal tangents, that was some information we did not need. Moving on. Let f be the function defined by this accumulation function. On which of the following intervals is the graph of f concave down? I want f to be concave down. So that means I want the second derivative of f to be less than 0, to be negative. So f of x is this integral. So what's f prime? Well, the derivative of an integral like this, the derivative and antiderivatives will cancel each other out. They're inverse operations, and we'll be left with 2x cubed minus 15x squared plus 36x. There we go. That's the first derivative. Now I need my second derivative. My second derivative is going to be 6x squared minus 30x plus 36. That looks like it factors. I'm going to factor out the 6 and give me x squared minus 5x plus 6. That looks like it continues to factor x minus 3 and x minus 2. Why is this useful? Because I want to know when f is concave down, when the second derivative is less than 0, when the second derivative is negative, right? So if the second derivative I have factored now, I need to figure out when it's negative. I can do my sign chart. What are the zeros over here? I got to put them in order from least to greatest. The zeros are 2 and 3. And my factors are 6, which is going to be positive all the way across, x minus 3, x minus 2. So we go ahead and say, all right, what is our sign chart going to be when x is less than 2? I have negative and negative, which makes this overall positive. This is my second derivative, remember? Between 2 and 3, say 2.5, I end up with negative and positive. Bigger than 3, everything's positive there. So when is my second derivative negative? That'll mean f is concave down between 2 and 3 only. All right, the function g is given by this function here. What is the absolute minimum value of g on the closed interval negative 2 to 1? Okay, absolute minimum. This means that we need our critical points and our endpoints. Then we need to plug them in and check them, right? So our endpoints are relatively easy to find. Our endpoints are x equals negative 2 and x equals 1, right? So I can plug those in, g of negative 2 and g of 1, and just figure out what our values are, because I want to find the minimum of g. So I plug it back into the function I'm trying to minimize. So negative 2 cubed is negative 8 times 4 will be negative 32 plus negative 2 squared is 4 times 3 is 12. Negative 2 times negative 6 is 12 plus 1 is going to give us 24. Negative 32 plus 24 is going to give us negative 8 plus 1 is negative 7. When I plug in 1, I'll get 4 plus 3 minus 6 plus 1, which is going to give us 7 minus 6 plus 1 is 2. All right, but I also got to check my critical points. So what are my critical points? Let's find the derivative. Critical points are where the derivative is 0 or does not exist. So my derivative is 12x squared plus 6x minus 6. That looks like it factors. I can factor out a 6. And that will leave me with 2x squared plus x plus 1, right? All right. Now I hope that this keeps factoring, and we'll keep working at it. All right. So still working at our derivative here. This will be 6. So I need to try to factor it into, okay, what are numbers that multiply to 2? I don't have too many options. 2x and x are going to have to be them. I need them to multiply to 1, to positive 1. All right. Need to multiply to positive 1. Oh, I changed the sign here, didn't I? This should be minus. Should be a minus 1 in there. All right, I need them to multiply to negative 1. So it's either plus 1, minus 1, or the other way around, right? All right, let's try minus 1, plus 1 to try to speed things up. Hopefully I've chosen right. Here we go. Just to check, make sure we get back here. 2x times x gives me 2x squared. 2x times 1 gives me 2x. Minus 1 times x, so I'd subtract x. That'll give me positive x. There we go. Sounds good. So what are my critical points? My critical points come from this thing I'm looking at here. My critical points then are x equals half from here, and x equals negative 1. Okay, so I need to now go and plug those things in. I need g of half. I also need g of negative 1. G of half is going to be interesting. That's going to be 4 times 1/8 plus 3 times 1/4 minus 6 halves plus 1. So what's that going to give us? That's going to give us, when we kind of simplify all this down, let's start running out of room here. 4 times 1/8, that's half, plus 3/4. 6 divided by 2 is 3 plus 1. So it's negative 3 plus 1, so minus 2. So getting common denominators here, this would be 2/4 plus 3/4 minus 8/4, which is going to give me 5/4 minus 8/4, or negative 3/4. All right. And then when x is negative 1, I plug that in. That'll give me minus 4 plus 3 plus 6 plus 1, which is going to give us 6. So I got lots of values to look at. I got 6 as a possibility, negative 3/4 as a possibility, 2 as a possibility, negative 7 as a possibility. What's my absolute minimum? My absolute minimum is negative 7. All right, and last one on this page. See, those absolute minimum maximum problems always take some time, but they are almost always there, and I can imagine it being something you get asked this year, so be ready. Okay, we're told f prime is greater than 0. So what does that mean? I'm just going to write notes. That means f is increasing for all x, and f double prime is less than 0. That means f is concave down, but it also means that f prime is decreasing, right? If f double prime is less than 0, f prime is decreasing. Which of the following could be the value, a table of values for f? Well, let's just see what's going to happen here. We'd be subtracting 1. Now we'd be subtracting 2. That means f is decreasing and decreasing faster. So our graph is decreasing and decreasing faster. So this is f prime is negative, and f double prime is, let's see, if we're concave down, that means f double prime is negative also. F prime is negative and decreasing. That's what we see the difference. It's negative, f prime is negative and decreasing. Then we're getting more and more negative. Here, 4, 4, 4, that means f prime is 0. It's a constant function, or at least it looks like it could be constant. Neither of those work for us. Here, let's see. 4 to 5 goes up 1. 5 to 1 goes up 1. So f is increasing, yes. But we need f prime to be decreasing. Our rate of change is 1 each time. This is kind of increasing linearly is what it looks like, not concave up or concave down. We want our f prime, our slopes, how much we're changing here, to be decreasing. They're staying constant. 4 to 5, we increase by 1, then we increase by 2. So looks like, yes, f prime is positive. Our slopes are positive. We're increasing, yes. Increasing by 1, then we're increasing by 2. We're increasing, but we're increasing faster. Our rate of increase is increasing each time. Here, increasing by 2, increasing by 1. So yes, f is increasing. The slope is positive. We are increasing. F is increasing. And it's increasing more slowly. That means f prime, our slopes here, are decreasing. This is what we want. All right. I want to walk through one other quick example here. I'm going to move pretty fast as an example for working with these things in free response questions, okay? For homework tonight, I'll go over it. The FRQs are optional, but I highly encourage you to do them. So let's take a look. Let's let f be this function here, defined on a closed interval, -3 to 4, with f of 0 is 3. Okay, so I already am noticing a few things. This sounds like an initial condition, probably going to be useful somewhere along the way. The graph of f, the derivative, so this is our derivative, make a label there so I don't make a mistake, consists of one line and a semicircle, okay? On what intervals is f increasing? Justify your answer. I like to justify first because it shows me what I need to look for. So I'll simply say f is increasing when f prime of x is positive. Now I know what to look for. That happens on the interval when is f prime, this graph here, this is f prime, when is it positive? Just from -3. I'm going to include -3 because -3 is positive up there. -3 till 2. Oh, sorry, -2. -3 to -2. That's when f prime is positive above the x-axis. -3 to 2. That's it. Okay. 1 point for your interval, -3 to 2. And 1 point for your reason here. F is increasing when f prime of x is positive. Now, if we want to be really specific, we could say that f, technically we're increasing all the way up to -2. That's what their rubric said that year, because even though it's 0 there, that's kind of when we stop increasing, when x is -2. But they don't care if you put a bracket or a parentheses there. All right, B. Find the x-coordinate of each point of inflection of the graph of f on the open interval -3 to 4. Justify your answer. So point of inflection, I can say f has a point of inflection when f double prime of x changes sign Yes. But how do I know that from f prime? Well, from f prime, what's our other definition of concavity stuff? I could say this then. That is when f prime changes. Remember, if f double prime is negative, that means f prime is decreasing. If f double prime is positive, that means f prime is increasing. So we can say that is when f prime changes from increasing to decreasing, or vice versa. So where does our f prime change from increasing to decreasing, or vice versa? Looks like at x equals 0, f prime changes from decreasing to increasing. We don't have to be differentiable there. We just need to change from decreasing to increasing, or vice versa. It looks like we also change from increasing to decreasing at x equals 2. So at x equals 0 and 2, that got you 1 point in your justification, because that's where f prime changes from increasing to decreasing, or vice versa. All right, C. Find an equation for the line tangent to the graph of f at the point 0, 3. Find the equation for the line tangent line. That means we need a point. That means we need a slope, right? We want an equation for the line tangent to the graph of f at the point 0, 3. Well, that's easy. They gave us 0, 3. That means we need the slope, which would be f prime of 0. So what is the derivative? What do I know about the derivative of f at 0? Here's my f prime graph. F prime of 0, when x is 0, f prime is negative 2. Remember, the y value here tells me the derivative of the graph, the original graph, at that x value. So f prime of 0 is negative 2. So I can write my equation, my tangent line. Y minus y1 equals m x minus x1. And you can just leave it like this. Remember, you don't have to simplify or change anything. If you wanted to, we could call this negative 2x plus 3 if you're feeling really, really gung-ho about it. All right, so 1 point just for your equation there. Part D was the kind of hefty one here, okay? It says find f of negative 3 and f of 4. Show the work that leads to your answers. So they're asking us about things on the original graph, right? Now this goes back to what I said at the very beginning of this lesson. If we want f of negative 3, if I want f of negative 3, that's going to be equal to, I'm given a derivative and I'm given an initial value. So f of negative 3 is going to be equal to that initial value, f of 0, plus the integral from 0 to negative 3, of f prime, like that, right? Because this will take my initial value and then add on to it. How much is f going to change from 0 to negative 3? This goes back to that formula we've learned before, which is that the final amount or value of something, I should say maybe f of b, is f of a plus the integral from a to b of the derivative. And look, we're given a derivative, we're given an initial value, so I can find what f of negative 3 is based off of that by combining them. So this is going to be, what do I know f of 0 is? I know it's 3. I'm going to add on the integral from 0 to negative 3 of f prime of t dt. All right. So how do I find that? That's an integral. I need the integral from 0 to negative 3. Okay, 0 to negative 3. That's all back over here. So let's see. What's the area of this triangle? It is a 2 by 2. So that's 4 divided by 2. So that area there is 2. What's the area up here? That's an area of half. Now I got to get my signs right here. So it's going to be 3 plus. As I take the integral, I'm going backwards and below. So this would be negative and negative. So that'll make it a positive signed area. I'm going backwards as I integrate this direction and above the x-axis. So that's negative, positive. So I'll make it a negative area there. So minus half. Okay. So I can just leave it like this if I want to for now. So this will be my answer here. If you want, you can say 5 minus halves. That's all the same thing as 9 halves. That's all fine. There we go. So that's the value of f of negative 3. But what about f of 4? What about f of 4? So f of 4 will follow a very similar pattern. I know what f of 0 is. I'm going to add onto it the integral from 0 to 4 of f prime of t dt. So what is f of 0? It's 3. We already saw that. Plus the integral from 0 to 4 of f prime of t dt. So this is going to be 3 plus. So what's my integral then? I'm going to change my pen color here. What's my integral then going to be from 0 until 4? This gets interesting, right? Because I have a semicircle here, but I need the area between the semicircle. I need like this section and this section. I need the area trapped between the curve and the semicircle. So I need to imagine then that I have a rectangle. The semicircle will be in here. I can find the area of the rectangle, subtract the semicircle, and that'll give me the leftover area. So what's the area of my semicircle? It's got a radius of 2. So it's pi r squared, which is 4, divided by 2. So the area of my semicircle is 2 pi. The area of my semicircle is 2 pi. So what's the area of my rectangle? It's a 4 by 2. So my rectangle has an area of 8. So to get the integral from 0 to 4, from 0 to 4, I can change color again just to remind you what that looks like. The integral from 0 to 4 then, which is starting here, goes all the way along up to there. So the integral up to there, which is this part, that is between the semicircle and the rectangle, is going to be the value of the rectangle, which is 8, minus the value of the semicircle, which is 2 pi. But notice we are below the x-axis. My areas I'm summing up are below the x-axis, so my signs need to be negative. So it's actually going to be subtracting that amount. So that looks silly. Let's go ahead and rewrite it like this. This is going to be 3 minus the quantity 8 minus 2 pi. Or we can say, I would just leave it like this, but if you want to, you can call it negative 5 plus 2 pi. And there we go. You got 1 point for finding your areas correctly, 1 point for finding the area correctly up here, 1 point for finding the area correctly down here, and then 1 point for your actual answer and actual answer using the fundamental theorem of calculus, initial plus the integral. All right. Hopefully that helps you get started. I encourage you, please go ahead and take a look at the homework, optional FRQs if you have time. There's 2 of them. I highly encourage you to do them. Good practice. But required tonight, I need you to go ahead on my website, fill out the individual study plan, see my instructions there for how to do that. Everyone needs to do that in preparation for this week. That is the required homework. Optional, take a look at the 2 for your response questions. I highly encourage you to do them if you have time. Please, please. All right. Talk to you later. Bye.